Yeah, let's get started maybe. So, hello everybody. My name is Johan Hadland. You can find me as jherland online, GitHub, Mastodon, Social, LinkedIn, elsewhere. I've been at NDC TechTown a few times before, but it's been a while and I'm happy to still see so many familiar faces here. For a long time, I was based in Oslo, and I first worked at Opera, and then I worked for Cisco at Lysaker. And both places I worked in embedded Linux and associated developer tooling. But 3 years ago, I moved to Delft in the Netherlands, and these days I work as a developer productivity engineer at a company called Tweak, which is part of the larger Modus Create software consultancy. At Tweak and Modus Create, we help our clients solve hard problems with open source software, and we also contribute back to the open source community whenever we can. More specifically, I work in the scalable builds group at Tweak, where we help speed up build systems and CI pipelines for our clients. And today I will talk to you about two developer tools that initially refused to work well together, and all the cool, the two cool and horrible hacks that we had to make in order to make the best out of the situation. It seems that code coverage maybe is a weak point in Bazel because Xavier Bonaventura, who had the previous talk in this room and give a Bazel introduction, he mentioned some problems with Bazel coverage, and you'll hear more about it here. Part of what I'll talk about today applies to these tools specifically, Bazel and Testwell CTC++. But there are parallels and lessons that certainly apply to lots of other tools as well. So I hope you'll learn something useful here, even if you don't work with these tools directly. Here's a quick overview of what we'll cover today. First, I will talk a little bit about the complexity and build systems in general, before covering Bazel and then Testwell CTC++ on their own. And then we'll get into the meat of the talk about how we made these two tools work together, and hopefully we'll have learned something at the end. So first, let's talk about complexity. In Systemantics, John Gall states, "A complex system that works is invariably found to have evolved from a simple system that worked." And he continues, "The inverse proposition also appears to be true. A complex system designed from scratch never works and cannot be made to work. You have to start over beginning with a working, simple system." So we can visualize this line between simplicity and complexity. And furthermore, we can imagine this invisible force, call it entropy or time or simply scope creep, that inevitably pushes us from simplicity towards complexity. But it's not that simple really, because there are two different kinds of complexity. There is essential complexity, so this is the complexity that is inherent in the problems that you're trying to solve. When you change something to solve a harder problem, then you're increasing the essential complexity of your project. And if you're solving this harder problem for a user, then you're providing more value to that user. And then there is accidental complexity. This is the complexity that creeps in when you're not looking. It often adds more problems than it solves, and it makes life harder for your users. If you look at something and you can call it complicated, then that is often a sign that you're looking at accidental complexity rather than essential complexity. One of my favorite quotes about accidental complexity is by a legendary computer scientist, Tony Hoare, from his 1980 Turing Award lecture. "There are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies. And the other way is to make it so complicated that there are no obvious deficiencies. The first method, of course, is far more difficult." Another quote is from Jamie Zawinski, an early Netscape engineer, in a 1997 Usenet post. "Some people, when confronted with a problem, think, 'I know, I'll use regular expressions.' Now they have two problems. It's not that regular expressions aren't useful. Some problems are indeed solved elegantly with regular expressions, and sometimes you could argue that they are indeed the best tool for the job at hand. But they do come with this trade-off, where you add the complexity of writing and maintaining the regular expression itself. So you need to be prepared to take on that complexity and the trade-off in terms of helping you solve a harder problem. That trade-off must be worth it." So our simple one-dimensional scale from simple to complex is not good enough. In fact, we need two axes of complexity, essential and accidental. We can talk about something being essentially simple or complex, i.e. moving around on the x-axis, or we can talk about the accidental complexity of something, i.e. moving along the y-axis. We still have the same pressure of the development cycle increasing the overall complexity of the system. But we can now start to think about maybe what kind of complexity we would prefer to add to a system. Can we increase the essential complexity without adding too much accidental complexity? Can we somehow hide the accidental complexity from the user? Can we solve a harder problem without making our product seem more complex? After all, as Brian Kernighan says in the epilogue to software tools, the purpose of most rewriting is to simplify a program, to make it easier to understand, to keep its complexity within manageable bounds. Controlling complexity is the essence of computer programming. So let's talk about build systems. We'll start by imagining the simplest possible build system, a shell script that simply lists out the sequence of commands that you need to run in order to build your project. For a very small project, this can be very simple indeed, maybe just a couple of lines to run a compiler on your source code. But when your project grows, so does this shell script. You add more commands, maybe you need to add some simple logic to deal with building libraries versus building executables. Maybe you start making different packages for different kinds of users. But pretty quickly, it becomes apparent that you need something more suitable than just shell scripts. So maybe you turn to something like GNU Make. With GNU Make, you're definitely adding essential complexity, because now you're defining build targets and dependencies, and you're unlocking incremental builds. But you're also adding some accidental complexity. Some of it might seem trivial, like Make's rules about tabs versus spaces in Make files, or the special variables with cryptic names that are somehow impossible to remember. But there's also more complexity that can sometimes surprise you at the worst moment, like the implicit and invisible rules that don't always do what you expect, or the issues that inspired an article that is called "Recursive Make Considered Harmful." You could try something different in GNU Make. Ninja is a more modern alternative that loses a lot of the old cruft from GNU Make. So as such, we can say that it solves the same fundamental problem as GNU Make, but it manages to do so with less accidental complexity. However, this picture is lying a bit, because one of the trade-offs with Ninja is that you're not really supposed to be writing your own Ninja files. Ninja is intended to read a build description that has been programmatically generated. So in addition to Ninja itself, you also probably need to write a script to generate that Ninja file. And this certainly adds some accidental complexity that is not shown here. Say that your project keeps growing and you need to deploy it on many different kinds of Unix systems. A very traditional option here would be to reach for GNU Auto Tools. This extends your GNU Make-based build with a configure phase at the start. And this phase looks at the build environment and it sets up your build based on what is available on your system. This adds a certain amount of portability and flexibility to your project's build system, so we're definitely further along on the x-axis of essential complexity. We're providing more value. But anyone who has worked with configure scripts, and especially if you dig into the M4 macro language of Auto Tools, they will certainly tell you that this also adds a lot of accidental complexity. A more modern build system would be something like CMake. This adds potentially even more portability to your project, and is generally more up-to-date with modern features of C and C++ toolchains of today. Still, writing CMake files is often a complicated project in itself, and you'd rather avoid doing it when you'd rather work on the actual project itself. We could keep talking about different build systems and placing them on this graph, but instead I want to talk about what kinds of features in build systems that pull us towards the right-hand side of this graph. What are the harder problems that build systems on the right-hand side of this graph are trying to solve? Of course, the first thing we encountered when we moved from the shell script to the make file, and often the first thing that comes to mind when you think about how to construct a build system, is the concept of targets and dependencies. This is what unlocks the incremental builds that many consider the cornerstone of any build system. But which dependencies do we actually want the build system to track? The obvious is the dependency relationships between the various source files and the artifacts produced by the build process. But what if you link with a system library? Does your build system know to trigger a rebuild if you upgrade that library? What about the tools and tool chains that you use to perform the build? With a new compiler version, would you not want to rebuild everything? And would you not want the build system to discover that? And then what about the build system itself? What if you update the build definitions or you upgrade the underlying build system? Is this actually automatically picked up by the build system, or must you apply some manual override to ensure a clean build? Next, there is one of the hardest problems in computing, caching. At the simplest level, is the build performed inside the source tree, or do you keep build artifacts separate from the sources? And only in the latter case, when you build out of tree, can you start to tackle the ABA problem. So this is where you have built a version A of your project, you check out version B and you build that, but then you check out version A again and you try to rebuild that. How much do you actually now need to rebuild? Is your build system smart enough to reuse artifacts not only from the last build, but a previous build? Can you cache those artifacts across multiple builds? Next is one of the big ones, multi-platform support. Does your project need to ship on multiple platforms like Windows, Mac OS, Linux, for example? Do you use a single build system to build for all three systems, or do you need to maintain 3 build systems in parallel, one for each platform? And with this comes another complication. Cross-compiling, or more generally, building for a different system or a different architecture than the build itself is running on. Another thing that we haven't really considered yet is the overall scope of the build itself, or the build system. Is the build system responsible for installing or providing the tools that it needs to run the build? Is the build system also responsible for setting up or controlling the build environment where the build actions are run? How do you make sure that variations in your local setup does not adversely affect the build result? And then once the build is done, does the build system also run your test suite? Does it prepare release artifacts? Does it even perform the actions necessary to deploy the actual release? Next, what about support for multiple languages? Many build systems only target a single programming language or a single ecosystem. But the popularity of monorepos means that it is increasingly common to find true polyglot code bases, projects that contain code in multiple languages that all go into some kind of unified build process. And once we start talking about monorepos and truly large code bases, then come the 3 big features that many modern build systems have started to tackle. The first one is sandboxing. Are you running build actions inside a strictly controlled environment to ensure that nothing from the external environment can pollute the build environment? But also that nothing from inside that build sandbox can adversely affect the build machines. It goes both ways. With proper sandboxing in place, it no longer matters where the build is actually run. Whether I run the sandbox on my machine or on your machine, we can be sure that the result should be the same. So we say that the build is hermetic and reproducible. And we can now reuse build results across machines. And this is further enabled by a remote cache. And this unlocks the final feature in many modern build systems, remote execution. You can now start the build from any machine, even a machine that is not powerful enough to complete the build itself. Instead, the build actions are distributed across machines in some data center. And the resulting build artifacts are stored in the remote cache, so you only need to download them after the build is done. So let's talk about Bazel. First, I should say that this is not a proper introduction to Bazel at all. For that, you should have been here in this room for the previous hour when Xavier Bonaventura gave exactly that introduction. He talked about the history and the fundamental concepts of Bazel, so I won't repeat much of that here. But Bazel's motto, if you go to its homepage, is this: fast, correct, choose 2. And I think Bazel chose this motto because many projects have this concept of a release build, which must always be correct, as opposed to an incremental build, where speed is prioritized, often over correctness. Bazel says, ¿por qué no los dos? Why not both? You shouldn't have to choose between a fast build and a correct build. However, when we remember that list of build system features that we just discussed, I would extend this to say, ¿por qué no los todos? Why not everything? Because Bazel actually supports everything on this list that I talked about earlier. I wish that that was all that I had to say about Bazel, and that I could simply place Bazel in this nirvana location of our complexity graph, the one magic tool that solves all the problems and has all the features without introducing any unnecessary complexity. Unfortunately, Bazel does come with quite a lot of accidental complexity as well, so let's look at some of that. Let's start with the most important feature in Bazel, actually. The reason that Bazel can claim to be both fast and correct is that it relies on aggressively caching earlier build results. Bazel has in-memory caches where it remembers the build graph so that it does not have to reparse the build definition on every single run. Bazel stores build results from multiple runs on your disk to be reused by later builds when inputs are unchanged. And then, of course, if you enable remote cache, there is an extra layer of caching in the network where Bazel can both download and upload build results, depending on your configuration. Of course, Bazel caches both intermediate and final build artifacts, but also in addition to that, Bazel has a concept of downloading external repositories that contain either third-party dependencies or build tools or extensions to Bazel itself, and these are also cached. Last year, we made a Bazel workshop for a client, and we drew this diagram to give an overview of the various caches in Bazel. But unfortunately, it's already out of date, because in version 8.3, Bazel added yet another cache, this repo contents cache, which is somehow different from the repository cache in ways that I won't even try to explain here and now. But in addition to all these caches, so Bazel has this embedded programming language called Starlark. You would use this language when you define your build graph in build files, and Xavier talked about this in the previous talk. You can also write extensions to Bazel itself in this language. Starlark is an almost but not quite Turing-complete language. It's heavily inspired by Python, although if you're very used to Python, there are some surprises waiting for you inside the Starlark language. There are good reasons for why Bazel has gone this way, but it is certainly not without a learning curve and some amount of frustration along the way. Next, the way that Bazel pulls in external extensions and third-party dependencies is changing in recent Bazel versions, and Xavier talked about this as well a little bit. I won't dive into all the details here, but there are some semantic changes that can definitely throw you for a loop if you need to migrate across this transition. A part of this transition from the old workspace file to bzlmod, which is the new scheme, is also the introduction of this Bazel central registry. This is sort of like a package management server for the Bazel ecosystem. So if you're familiar with PyPI in the Python ecosystem or crates.io in the Rust ecosystem, then this is the same, except it's for Bazel. Next, as we all know, there are two hard problems in computer science: cache invalidation, naming things, and off-by-one errors. We've already talked about caches, so let's talk about naming in Bazel. Bazel has a scheme and syntax for how targets are named, and it can get quite involved. Especially when you combine this with how external repositories are named in Bazel, you can get some quite complicated names. The red part of this command line is a single target name in Bazel, and I can assure you that it is not a name that we chose intentionally. Not only are the names themselves complicated, but there are also separate namespaces for each external repository, meaning that sometimes the same dependency can have different names depending on where it is referenced. Or sometimes what looks like the same dependency in two different namespaces can end up pointing to two different things. Lastly, I want to mention a couple of things where I frankly wish that Bazel had done a better job. The first is what I think are some bad defaults that makes it harder than it should be to achieve Bazel's ideal of an hermetic and reproducible build. Because when you start using Bazel to build C or C++ code, Bazel will happily find whichever toolchain that happens to be installed on your system and use that. You don't need to configure or specify anything for this to happen. It just works out of the box. But this comes back to bite you when you want to scale your build up to run remotely. In order to succeed at that, your build must be safe to run in that remote build environment. That is, it must be hermetic so that build results can be reliably reproduced on the remote machines. And this is where you will want to avoid using whatever toolchain is installed on your system. Instead, you typically want to ensure that all tools and toolchains involved in the build are precisely known and even controlled by Bazel. And finally, another annoying part of learning Bazel is the insane amount of command line options available. A company called Engflow that is quite active in the Bazel community had some fun a while back, and they produced this card deck where each card documents another Bazel option. But the joke's on them, really, because not only is the card deck already out of date, you would need almost 30 additional card decks to cover all the command line options in Bazel. On Bazel's main branch today, there are about 1,500 command line options, and about 1,000 of these are documented on the Bazel website. So you'll find yourself searching that website fairly often. The reason for this is that Bazel has chosen to expose every configurable setting and switch in its command line interface. Fortunately, though, the command line interface doubles as the configuration language, so you'll be using the same options when you write your Bazel RC file to configure Bazel for your project. So I think the reality is a little bit closer to this. Bazel definitely sets out to solve a harder problem than most other build systems. It supports a lot of advanced features and scenarios that other build systems can barely dream of. And for those that need most or all of those features, it is definitely a worthwhile investment. But it certainly does not come for free. Bazel has a challenging learning curve, and migrating a project to Bazel is often the start of a long journey. Anyway, let's move on to the other star of the show, CTC++. CTC++ is a code coverage analyzer that was originally developed by Testwell, a Finnish company that, with its roots in Nokia. And Testwell later got acquired by VerifySoft, a German company, and CTC++ is still being sold and supported by VerifySoft. I do want to emphasize that there is not necessarily anything too special about CTC++. There are other tools that behave in similar ways and that could have maybe taken the place of CTC++ in this presentation. Coverity is one example of another static analysis tool that raises some of the same challenges when integrated with Bazel. But CTC++ was a tool that we were asked to integrate with Bazel, so that's what I'll talk about today. As a code coverage analyzer, CTC++ works in a similar way to other code coverage tools. It instruments the code at build time so that it can count what functions or statements or expressions are being executed at runtime. Then, when you run a test suite to execute that code, those coverage counters are collected. And you can then compile a separate coverage report that shows which parts of your code were executed or covered by your test suite. This is a very useful tool for developers, and in many organizations and industries, it is even a requirement as part of the software development lifecycle. So, to quickly recap. Here is our typical build and test sequence without code coverage analysis. We start with some source code, which is compiled into object code, then linked into an executable. Finally, we run some tests with that executable, and we get some test results. With CTC++ code coverage, here is what changes. Instead of running our compiler, we run the CTC++ compiler instead. CTC++ wraps our other compiler, but it first makes sure to add coverage instrumentation to our pre-processed source code. CTC++ also writes out this extra file called mon.sim, which contains some bookkeeping information for CTC++. And then at link time, we run the CTC++ linker instead of our linker. Again, this wraps our linker, but it adds this additional CTC++ library, which becomes part of our executable. Finally, when we run the tests, the instrumentation inside the source code, together with the CTC++ library that was linked in, will count up all the coverage statistics and write them to this separate file called mon.dat. Of course, we also get the test results from running the tests. Finally, after all of this, we can then run the CTC++ report tool, passing in the mon.sim and mon.dat files. This will generate a nice HTML report where we can browse the source code and see how many times a given function or line or expression was executed. And since the source code is embedded in the HTML report, the CTC++ report tool also needs access to all the source code. If you have done coverage testing before with C or C++, you might be familiar with a tool called gcov or lcov. So how do these differ from CTC++? Well, in principle, the mode of operation is quite similar. CTC++ wraps the underlying compiler, but it is otherwise independent of it. gcov, on the other hand, relies on coverage instrumentation built into GCC or LLVM typically. Otherwise, these differences are mainly file formats and what extra bells and whistles are offered by the different reporting tools. So, let's start looking at how we can get Bazel and CTC++ to work together. First, I should note that there is, in fact, built-in support for coverage analysis in Bazel. There is even a dedicated Bazel subcommand for it, Bazel coverage. However, as soon as we started looking at this, we discovered some problems. Bazel's coverage support depends on your toolchain configuration already having exposed support for building with coverage instrumentation. This essentially ties it to the gcov workflow, where the instrumentation is already built into the compiler. There are also assumptions about the file formats and the naming of the files associated with coverage testing. And finally, even if you do end up working with Bazel's built-in coverage support, there are some complications and limitations when combining it with Bazel's caching of test results or with remote execution. More details are in that link at the top. So, would it be possible for us to integrate CTC++ into the existing coverage support in Bazel? No, not really. We couldn't convince Bazel to work with a different coverage file format than GCOV's format. Nor could we convince CTC++ to use a different file format than its own. And we were also stuck at substituting CTC++ into our current Bazel toolchain without messing up the toolchain for non-coverage use cases. And finally, we couldn't find an easy way to handle these extra outputs generated by CTC++ within the confines of the existing Bazel toolchain configuration. In addition to not being able to reuse Bazel's existing coverage support, we discovered a couple of other things when we started to dig into the details. First, the files that were generated by CTC++ were not at all reproducible. When we built the same thing twice with CTC++, there would be lots of changes in those mon.sim and mon.dat files. We started looking at the mon.sim file in particular, as it was in some kind of text format, and we recognized 3 different things that were distinctly not reproducible. There were embedded timestamps that changed for each compilation. There were lots of absolute paths to source files. And even worse, those paths were pointing into the Bazel sandbox and would thus become invalid as soon as the sandbox was removed. And then there were some 32-bit values that sort of looked like, or we suspected that they were some kind of checksum or fingerprint. The mon.dat file had similar problems, but this was also in some binary format that was much harder for us to decipher. There was one more factor that fortunately made our task here a little bit simpler. When the client asks us to look at integrating CTC++ and Bazel, they were only running CTC++ coverage analysis on occasional nightly CI builds. So we just had to make Bazel and CTC++ work together somehow. It did not have to be especially fast, and we did not have to support impatient developers that were used to incremental builds. So, let's describe what we did here. We started by configuring a new toolchain for Bazel. This toolchain uses CTC++ as the compiler and linker. Or rather, it calls a wrapper script that we wrote in order to allow us to configure and adjust the options and environment for CTC++ per compilation unit. And one of the things our wrapper script does is, of course, to configure CTC++ to wrap our real compiler. So it's basically wrappers all the way down. So what do we do about the mon.sim and mon.dat files? Nothing really. We treat these as side effects of the build and test phases respectively. They are not tracked by Bazel. And since they are appended to by each and every compile action or test run, there is no real way that we could even track these with Bazel. Because Bazel thinks in terms of this action is going to need these inputs and it will create that output file. But these files are the result of many subsequent actions. So in order for this to work at all, we need to apply some extra rules to the overall coverage build process. We need coverage builds to always be performed in full from a completely clean slate. That means disabling all of the build caches, disabling remote execution, and also disabling Bazel's caching of test results. The consequence is that there is 0 reuse between coverage builds, and it takes the better part of an hour to complete a full build and get a coverage report. Not something that any developer would want to run frequently on their own machine. If you're interested in exactly what this solution looks like, for example, how we define the new toolchain, what our wrapper script looks like, or our Bazel configuration, I can refer you to this blog post from a couple of years ago that has all those details. But before we move on from this initial approach, let's detail some of the side quests that we also faced, just to get Bazel and CTC++ to work together at all. Specifically, the challenges posed by running CTC++ from within the Bazel sandbox. First, these mon.sim and mon.dat files are considered side effects. They are appended to by CTC++, while the primary task is to either produce a compiled object or a test result. So in order for the appending to work at all, these files must live outside the sandbox, because with the sandbox, there is one sandbox per compilation unit. And in order for CTC++ to successfully write to them, we must ask Bazel to poke a hole in the sandbox to allow those writes to happen. Next, a similar hole needs to be poked in the sandbox in order for CTC++ to run at all, because CTC++ performs this license check on startup, and that needs to access a license server in the network. Network access is something that we usually disable inside the sandbox. So in order to improve, and we do that to improve hermeticity, but here we needed an exception. Then we're getting to the interesting part. While working on all of this, we noticed that the CTC++ report tool would occasionally complain about the mon.sym file being corrupt. And we would get coverage reports that were obviously incomplete. We further observed that this only seemed to happen when A, the same sandbox was enabled, and B, when we were building with multiple threads. After some more digging, we suspected that some temporary files used by CTC++ were being corrupted when there were multiple CTC++ compilations running concurrently. And in the end, we found the following. While CTC++ is running, it makes use of some temporary files that are put in /temp by default. But CTC++ is careful to use the current process ID when naming these files, precisely to prevent concurrent CTC++ processes from using the same file names. So this really shouldn't be a problem. However, Bazel throws a spanner into the works, because Bazel's sandbox uses a PID namespace to ensure that processes inside one sandbox cannot see processes in other sandboxes. And this PID namespace causes the PIDs inside of each sandbox to restart their numbering from 1. So the build process inside each sandbox has a rather predictable and repeatable PID, which means that CTC++ processes sometimes end up choosing the same name for their temporary files. Furthermore, Bazel, by default, does not isolate the /temp folder between sandboxes. So all sandboxes share the same /temp. So we end up with simultaneous writes from concurrent CTC++ processes into the same files in the same /temp folder, and this corrupted data is then being copied into the mon.sym file. The solution we landed on here in the end was to direct CTC++ to write its temporary files inside the sandbox instead of /temp. And then this immediately resolved the corruption. Finally, another complication introduced by the Bazel sandbox is that the source file paths that are recorded inside mon.sym reference the source files as they appear inside the Bazel sandbox. These sandbox directories are created and deleted by Bazel before and after every single build action. So the source file references are immediately invalid, and the CTC++ report tool cannot find the source code listings needed for the report. Fortunately, though, the CTC++ report tool comes with an option that allows the source code references to be mapped back into persistent or real source paths. So we use that, and even though the sandbox paths are present in the mon.sym file, we can map them back to real paths and fix them up, and the report can be generated successfully. So we ended up making something that works, sort of. It's certainly not ideal. In order to make it correct, we had to basically disable everything that makes Bazel fast. So we're definitely not living up to Bazel's motto of being correct and fast. But this was sufficient to get regular coverage reports generated by a nightly CI job. So mission accomplished, I guess. Because of the side effects of appending to mon.sym, we cannot leverage the Bazel cache, but this wouldn't really have helped us anyway, because the coverage outputs are, first of all, they're different from the regular build outputs, so there's no point in sharing cached objects between coverage builds and regular builds. But moreover, the CTC++ outputs are not reproducible. So we could not reuse them even if they were cached. They're just not worth caching at all. Anyway, here are some timings from this first chapter in our saga. A full coverage build and test run takes over 30 minutes. And together with the time needed to compile the report, we're almost at 45 minutes. The project consists of several applications, and if we limited the build and coverage analysis to one of these applications, we could get some quicker results. But this was the cost for every single build, as there is zero reuse from one build to the next. So let's fast forward a few months. Our client came back to us, and now they really wanted CTC++ coverage analysis to be more directly accessible to developers. We had to make this both fast and correct. So this time we really had to make it work with the Bazel cache. So let's re-examine the fundamental impedance mismatch between Bazel and CTC++. The Bazel cache is all about reusing previous build results when inputs have not changed. But what is it that we actually want to reuse? Well, let's focus first on what happens at build time, because this is where most of our time is used in any case. We want to reuse the build artifacts that are generated during a build. That means the object files that are unchanged since the last build, but also libraries and even executables when there is no need to rebuild them. But we also need to reuse the symbol file that CTC++ generates. If we look at what happens at runtime later, we could make a similar argument. We want to reuse test results for tests that are unchanged, but also we want to reuse the accompanying counter data from those earlier test runs. Anyway, let's focus on the build time for now. And let's distill our quest for reuse into two main questions. First, how can we capture and successfully cache the extra CTC++ output, the mon.sim file? And next, how can we make the build outputs, including the symbol file, reusable? And by that, I really mean reproducible. So actually, let's start with the last question first. How can we make the CTC++ outputs reproducible? Well, we probably need to redact or rewrite those timestamps in the symbol file, and redact or rewrite the absolute paths that point into the temporary sandbox, and also redact or rewrite those 32-bit fingerprints that we found. But it's not only the mon.sim file that is problematic. If we stop the compilation process right after the pre-processed source code has been instrumented by CTC++, but before it's sent to the real compiler, then we can look at the instrumentation that CTC++ has added. And what do we find? We find the same timestamps, the same absolute sandbox paths, and the same fingerprints as in the symbol file, but this time in the instrumented source code. There are lots of other stuff related to actual coverage instrumentation, of course, in that file too, but all of that appears to already be reproducible. The problems are these same pieces of non-reproducible data that occur in both the symbol file and the instrumented source. And since the instrumented source is not reproducible, that means that the final executables are also not reproducible. And the counter data that is written to mon.dat is not reproducible. But if we can fix the non-reproducibility here at the source, then we can probably make all of this reproducible. So what tools do we have at our disposal to do this? Well, remember that we're already wrapping the CTC++ compiler, so we can insert some tricks right before or after the CTC++ compiler is run. We can access the outputs from CTC++ while they are still in the sandbox and before they're picked up by Bazel and moved along in the whole build process. We can also configure CTC++ per invocation, and we found out that we can actually tell it to write to a separate mon.sim file per compilation unit. So we're no longer appending everything to the same file. Instead, we're writing one symbol file per compilation unit. But we also have another trick up our sleeve. CTC++ allows for these hook scripts to be configured, and these scripts will then be invoked by CTC++ at certain stages while CTC++ is running. Specifically, we can use the run after CPP hook to give us, and that gives us access to the pre-processed source code, but just before CTC++ adds its own instrumentation. And there's also a run after instr hook that gives us access to the instrumented source right before it's handed off to the real compiler. So what can we actually do with this? In the run after CPP hook, we can calculate our own 32-bit fingerprint that is only based on the pre-processed source. Remember that this preprocessed source is reproducible because CTC++ hasn't yet added its instrumentation. And also, after a couple of meetings with VerifySoft, they have told us that although this fingerprint is not calculated in the same way as their own fingerprint, it is likely good enough for our use case, and it will not cause problems as long as we use it consistently. So we have this new fingerprint, but CTC++ hasn't added the instrumentation yet, so where do we put this fingerprint? Well, this is where the next hook comes into play. In the run after instr hook, we can access the source code after CTC++ has added its instrumentation. The instrumentation is a collection of preprocessor macro calls that is quite straightforward to parse. So we do just that. We find anything that looks like a source path pointing into the sandbox, and we rewrite that so that it's relative to the root of the source tree instead. It becomes a stable path. We find the timestamps in that CTC++ inserts, and we rewrite them all to a static timestamp instead. Again, from VerifySoft, we have confirmation that this does not affect the coverage calculation itself. It only affects, the only effect is that these dummy dates will show up in a couple of places in the final report. And finally, we find the fingerprint that CTC++ has calculated, and we substitute our own fingerprint that we calculated above. This takes care of the instrumented source code that gets compiled and ultimately ends up in the test executables and written into the counter data. But it does not change what CTC++ writes into the symbol file. So we need to do the same reduction process to the symbol file. So in our compiler wrapper script, first, as I mentioned in the previous slide, we instruct CTC++ to write a new sim file inside the sandbox instead of appending to one huge mon.sim file. And then, right after the CTC++ compiler has finished and the symbol file has been written, we can now perform the same reduction process on the symbol file. The format of the symbol file is different from the instrumented source code, so the parsing looks a little bit different, but what we're essentially doing is the same. We find and rewrite the source paths, we find and rewrite the timestamps, and we find and rewrite the fingerprints. So we have now a symbol file and an instrumented source that matches and that is reproducible, because we have rewritten all the non-reproducible parts. If we rerun the same compilation at a later time on a source file that has not changed, we will calculate the same fingerprint again. We will rewrite the variable sandbox paths with stable paths referencing the source tree. We will replace the current timestamp from CTC++ with our static timestamp, that is the same as last time. And we will replace the fingerprint from CTC++ with our own stable fingerprint. And since the instrumented source is now reproducible, then so is the resulting object file. So at the end of all this, we have a reproducible object file and a corresponding and reproducible symbol file for each compilation unit. But we have created another problem here, because Bazel only preserves the object file from the sandbox. The symbol file is about to disappear with the rest of the sandbox as soon as this compilation unit is done. So this nicely leads us to the other question that we need to solve. How can we capture and cache the extra CTC++ outputs, specifically the symbol file? From the previous slide, we've changed the question a little bit, because now instead of having a single mon.sim file accumulated from all compilation units, we have many small symbol files corresponding to each compilation unit. These symbol files are directly related to the corresponding object files. So if we cache and later reuse an object file, then we really should do the same with a corresponding symbol file. So can we make Bazel regard these two files as a single unit? Well, we can if we bundle them into the same file. The object file, after all, is already in the ELF format, and we can actually use this format as a container for more data. This obj_copy command allows us to add a new chunk of data called an ELF section into the object file. We give this section a name, CTC sim, so that we can extract it from the object file later. The default flags that apply to this ELF section means that the new section will not be loaded into memory when code from this object file is executed. It will also not interfere with the code or any other sections in the object file later, luckily. However, the object file does become a little bit bigger. But also, the object file is not the ultimate output of our build. Object files are linked together into libraries and executables. And ultimately, we want, from a final test executable, to be able to extract the symbol file data that corresponds to all the objects that went into that executable. To achieve this, we must also add an additional step to the linking phase. When object files are linked together, we extract the CTC sim section from all the object files that go into that linker process. We concatenate them all together into a new, larger CTC sim section, and then we re-embed that CTC sim section into the linker output. Fortunately, the library or executable that we're getting from the linker is also in the ELF format, so we can basically do the same trick here. Then, once we have run the tests, we can now extract the CTC sim section from the test executables or from any libraries that the test depends on, and place the resulting symbol files next to the counter data that were also generated when we ran the test. And we can give all of this to the CTC++ report tool, and we can generate a report. And this is really the gist of it. With this hack in place, what Bazel sees is a compilation process that generates reproducible object files, just like what Bazel expects. Bazel does not care that these object files have this extra ELF section inside. So we can now re-enable the Bazel cache, and Bazel will cache and reuse these object files, libraries, and even executables. In the same way that it caches and reuses any other intermediate or final outputs from a previous build. So that takes care of the build time cache. But we haven't really touched what happens while the tests are run yet. The counter data is still appended into a single mon.dat file outside of the sandbox, and it can therefore not be cached by Bazel. So we still always need to run all our tests from scratch in order to get complete counter data. Bazel's caching of test results has to remain disabled for now. Fortunately, running the test suite and running it from scratch is much quicker than building from scratch. And we still actually haven't gotten around to implementing the caching of counter data, but it would roughly follow the same lines that we've already outlined here for the symbol files at build time. You could say that we've left that part as an exercise for the reader. So the last slides covers a lot of ground. Let's recap what is actually going on here with an illustration. First, this is what things looked like after our initial solution was implemented. So we start with the compilation process. We have some source file that goes into the CTC++ compiler, which preprocesses, instruments, and compiles that source into an object file. And that object file is not reproducible. While that is happening, CTC++ also appends this symbol data into this mon.sym file, which lives outside of the sandbox. Next, in the linker phase, we take all the object files that goes into the link, passes it to the linker, we get a test executable out on the other side. Since the inputs are not reproducible, then the output is also not reproducible. And then we run those test executables at runtime. We get a test log, we get a test result, but also the instrumentation appends the counter data into this mon.dat file that also lives outside of the sandbox. And then after all of this is done, we can take those two files, pass them to the report generator, and we can get our HTML report. So this is basically what we were doing after the first phase. This is what ran in CI on occasional nightly builds. And then, what does this look like after our horrible hack? Sorry, wrong slide. Here's what our second solution looks like. So now, we still have the compilation process. We still run CTC++. CTC++ preprocesses the source code, and then it invokes our run after CPP hook. This looks at the preprocessed source code, and it generates a fingerprint that is stable and reproducible. And then CTC++ moves on. It instruments the source code. We get to our run after instr hook, at which point we take the instrumented source code and we rewrite these parts of the instrumented source code to make it reproducible. This is then passed to the compiler, and we get a foo.o file. And next to it, we get this foo.sym file inside the sandbox this time. And these are now both reproducible. Except, well, the symbol file becomes reproducible after we do the same rewrite to that. And then finally, we take the rewritten symbol file and we embed it into the object file with this CTC sim section. And we now have a foo.o object file that is reproducible and has symbol data embedded inside of it. Then at link time, we take the object files, pass them to the linker, we get a test executable. But we also need to extract these CTC sim sections, concatenate them together, and then embed them back into the test executable so that we carry forward all the symbol data into the final test executable. Then at test runtime, we run the test, we get a test log, we get a test result, and we can then, and also while the test is running, the counter data and instrumentation inside the test executable is getting accumulated into this mon.dat file outside of the sandbox. And after that is done, we can now take the test executable, extract the CTC sim section, and write out the symbol files that went into that executable. And finally, we can pass all of this to our report generator, and we can get an HTML report. But this time, it's based on reproducible data. It is based on object files that can be reused from one build to the next if they haven't changed, or even full test executables. So what have we actually learned here? Let's look at some results first, comparing our second solution to our first solution, where we always did coverage builds from scratch. First, here is the worst case scenario. So this is our second solution, but for the case where the cache is empty or when a full rebuild is actually needed. We can see that there is pretty much no speed up, modulo some noise, and this is exactly what we'd expect. We are in fact doing the exact same amount of work in total here. We're doing a full build. There might be some extra overhead, in fact, with all the extra symbol file manipulation that we're doing, but this doesn't appear to affect the overall build time. Next, here is the best case scenario. That is when all the outputs are unchanged since the last run, and we can reuse everything. In this case, we still need to rerun all the tests since we cannot cache those yet. and we still need to regenerate the coverage report. So that is basically what we're seeing in this table. The actual build time is 0 since nothing needs to be rebuilt. And the overall speed up is significant, exactly what we would hope. But this scenario isn't very common. You seldom run a build and it's exactly 100% identical to the previous build. A much more common case is that you have a developer that has made some changes to a limited part of the source tree, and then they rerun a coverage build to see how their changes have affected the test coverage, either by rebuilding the entire source tree or by rebuilding the application where they have made changes. Here, some parts of the code are being rebuilt, and the affected tests have to wait for this to complete before they can be rerun. But for all the parts of the code that didn't change, Bazel can immediately start rerunning those tests. Thus, some of the rebuilds happen concurrently with other tests running. And since our total build plus test time is now dominated by the test runs, the cost of these rebuilds kind of disappear into the test run times. So we still end up with a significant speed up, and the total time remains dominated by running tests and generating the report. So what is left to do here? Obviously, we should apply the similar scheme to the test runs so that we can bundle counter data together with the cached test results, and we can then enable Bazel's caching of test results and save more than half of the remaining runtime when only a small portion of tests need to be rerun. That said, the changes we have made at build time have obviously had a much bigger impact than we could get from this future work. Throughout this process, we have had productive discussions about CTC++ with VerifySoft. VerifySoft remains hands-off in terms of supporting specific build systems. They want to stay build system agnostic, so they're not looking to add support for Bazel specifically. However, they have said that they will work on a new feature to allow CTC++ to rewrite or shorten paths at instrumentation time. And that this will make it possible for us to have CTC++ include stable and reproducible paths in their instrumented source and symbol files. This should also make their fingerprints reproducible, although, as far as I understand, we would still need to redact the timestamps. And then bundling the symbol files into the object files, that is a hack that will likely remain, because that is less about CTC++ specifically and is more about meeting Bazel's expectations for what a compiler outputs that Bazel keeps track of. So, in the end, we have actually achieved what we set out to do. We leveraged the Bazel cache to avoid unnecessarily rebuilding of coverage instrumented source code. It certainly involves a fair amount of added accidental complexity in the build process, mostly in order to make the outputs from CTC++ reproducible and reusable by Bazel. But the end result in the common case is a roughly 5 times speed up of the total time needed to build and test with coverage instrumentation, including the generation of the final coverage report. And furthermore, we think that this is a good example of how to take a tool that does not play well with Bazel's idea of hermetic and reproducible build output and force it into a shape where we can then leverage Bazel's strength. The details might be quite ugly, but we're quite happy with the end result. I'll leave you with this quote from Paul Anderson. I've yet to see any problem, however complicated, which, when you looked at it in the right way, did not become even more complicated. And that's it from me, really. Thanks for listening. If you think that this talk should rather have been a blog post, then you're absolutely right. In my post on the Twig blog, you can find everything from this talk, plus even more details and links to more sources. More generally, on the Twig blog, you can also read about all the other things that Twiggers are up to. And if you want to work with build systems and improving the developer experience, then please apply to our Scalable Builds group at Twig. We're hiring. And if you want to learn more about Twig or Modus Create, then here are those links as well. And if you want to reach me again, I'm Jay Herland online. And with that, I'm happy to take questions, and you can always find me afterwards if you want to discuss more. So, any questions? Yes?
Is there a way for Bazel to natively recognize the sim files?
There probably is, or there surely is. Bazel is very extensible, but the details get really complex really quickly. We briefly looked at implementing what is called an aspect in Bazel to basically take the build graph in the non-coverage scenario and then sort of manipulate the build graph to say that oh, for all build steps, there is now also this additional output, and you need to keep track of that. But then you also need to tell Bazel that it needs to be tracked under the same regime that it tracks the object file, so that when you reuse the object file, the symbol file also gets reused. And you never will get into a situation where Bazel says that, oh, I will take the object file from here, but now I need to regenerate the symbol file. Like, you never want to get into a situation where it finds one but not the other one. So that's basically why we ended up saying that actually it's easier for us if Bazel just sees the one file that it expects, and we just embed everything into there. Then we're 100% sure that you always get the symbol file with the object file. It's always from the same build. You will never have a problem where you're missing one or the other. More questions? If not, we still have, we can take lunch 5 minutes early. Thanks for listening.